This video is going to show how the Laplace transform is affected by shifting and how some shifting is induced by the Laplace transform. So to start the discussion, let me remind you that many times we describe the Laplace transform of something as capital F of S because the notation itself does not indicate that it's a function of S. But as you'll recall, this is the integral from 0 to infinity, e to the negative st f of t dt. So whatever goes in these parentheses here go into that spot up there. Remember, this is a function of S. That's why this notation is sometimes desirable. So let's start off with a being some sort of a positive number. So let a be greater than 0. Then when I look at and replace s with s minus a, in the integral itself it'll go from 0 to infinity, but I'll have e to the negative. Now s is replaced by s minus a. And let me just do a small amount of simplifying. I'll have e to the negative st plus at f of t dt. And then I'm going to break this up into e to the at times e to the negative st f of t dt. So you notice this is close to what I want. Let me go ahead and rearrange these things. I think I have it backwards from what I actually wanted. 0 to infinity, I'll have e to the negative st. I'll put my dot there this time, so I have e to the at f of t dt. And you'll notice here that e to the negative st is always what you have in front of ft. Whatever is after e to the negative st goes in the curly brackets for the Laplace transform. Here then, if that's the case, then e to the at f of t goes in the curly brackets. And so this is the Laplace transform of e to the at f of t. And you'll also have to notice that every time we develop a formula, we're also going to develop an inverse formula. So this, let me put it over here, f of s minus a equals this. Then the inverse Laplace transform of f of s minus a will take you back to e to the at f of t. Let's do a few examples. Let's take a look at the Laplace transform of t e to the negative 6t. I'm going to put it more like this, so I'm going to rewrite it as the Laplace transform of e to the negative 6t times t. Now, according to this, it should equal f of s minus a. Now, the Laplace transform of just t was equal to 1 over s squared. So, this is what they're talking about here. This here is my f of s. So now this says that f of s minus a, and the a is whatever is in front of t here. So here I'm going to have f of s plus 6, but my f of s is 1 over s squared. So that'll be 1 over s plus 6 squared. I'm going to fire off a few examples in a row. Next we have the Laplace transform of e to the 2t times t minus 1 squared. Now, in order to make use of this, here my a is a positive 2, so I'll have an f of s minus 2 when I get down to that. Now I got to figure out the Laplace transform of t minus 1 squared. For these, you just have to break it up or multiply it out using the FOIL method. T squared minus 2t plus 1. And that equals the Laplace transform of t squared minus 2 times the Laplace transform of t plus the Laplace transform of 1. And so the Laplace transform of t squared is 2 factorial all over s cubed. And then I have minus 2 times the Laplace transform of t is 1 over s squared. And then finally I'll have 1 over s. So this version is the f of s version that I'm thinking of. And so according to this, I have to shift, if you will, to 2. Or I'll have to change my s's to s minus 2. So this equals 2 factorial. I'll leave it there just so you know where it comes from later on. But instead of an s, I'm going to shift s minus 2. This is, if you will, this is a shift to the right 2 units. Minus 2 over s minus 2 squared plus 1 over s minus 2. For my next example, let's do the Laplace transform of e to the negative 2t cosine of 4t. Now on these, you're not shifting to the right by 2, but you're shifting to the left 2 units. So you'll have an f of s plus 2 as part of this problem. First thing we need to do is figure out the Laplace transform of 4t, cosine of 4t that is. And that's the one that had an s up here, and then we had s squared plus 4 squared plus k squared. So according to this, wherever you see an s, I'm going to replace the s with s plus 2. Now on the way back, for reversal, a couple of reverses, we'll have, give me the inverse Laplace of 1 over s minus 4 squared. And we kind of have to work from a base of 1 over s squared. So normally, let's take a look. For one thing, I know that the inverse Laplace of 1 over s squared equals t. So now, what is this? This shifting to the right by 4. What happened then? Well, that must have come from something that was shifted 4 to the right. So in other words, this equals e to the 4t times t. Where am I getting the e to the 4t? Because if I take, I didn't mean to have that inverse in there. If I take the Laplace transform of e to the 4t, the Laplace of t is 1 over s squared, and then the 4 here tells you that you would have to shift it to the right 4 places. Here's a much more complicated example. let's say we have the Laplace transform of 2s plus 5 all over s squared plus 6s plus 34. Now, one of the things you need to do is you need to start looking at a table of Laplace transforms to see where you're trying to get to. But in general, what you want to do with something like this is to complete the square in the denominator. And I'll show you what that means. In the denominator, you may have remembered something like s squared plus 6s. And then I want to figure out what I need to add to 6s, to this part here, to get a perfect square. And you might remember that that's 1/2 of 6 squared. So I'll go plus 1/2 of 6 squared. I'll go 6 over 2 squared. But you also, since you just added that in, you also have to subtract the exact same thing off. And then I'll have my 34 out here. So that equals the inverse Laplace of 2s plus 5 divided by, now 6 over 2 is 3, so I have s squared plus 6s plus 9. That is s plus 3 squared. And then what do I have left? I have 34, but then I have minus 3 squared, so I have 34 minus 9. I have plus 25. Now, what you always want to do is break this up even further. You see that I have the s plus 3 here and plus 25. This fits the format of those Laplace transforms that had an s squared and a k squared. Up here, that remains to be seen. What I typically will do then is use the linearity of this inverse transform to rewrite it as 2 times the inverse Laplace of s over s plus 3 squared. And instead of 25, I'm going to write it as 5 squared so that I can recognize it in the Laplace tables. And then I have plus 5 inverse Laplace 1 over s plus 3 squared plus 5 squared. Now we're going to try to figure out, I can't quite use an inverse Laplace yet unless I match this s plus 3 with an s plus 3 up here. So that's what I will do. I will simply put s plus 3 there. So long as I subtract off the exact same thing. And then here, don't forget the plus 5. Let me move to the right a little bit so I can capture all this. 1 over s plus 3 squared plus 5 squared. Now if you notice, these have exactly the same denominators. Here I have a negative 6 if you pull the 2 in, and I have a plus 5, so I'm going to take all this and make it minus 1. And now let me just remind you of something. We had that the Laplace transform of cosine of kt equals s divided by s squared plus k squared. So you can see ours fits the bill, s over s squared plus k. The k in this case will be 5, except the s has been replaced with an s plus 3. So that means there has been a shifting to the left here, 3 units. So that part there, let me kind of get this, merge this off. Let me see what we were working on here. I'll come bring this down. So here we can see that from this shifting here means that I have to have, remember, e to the at results in s minus a. So this is like s minus negative 3. So I'll have 2 e to the negative 3t, and then I'll have cosine of 5t. Now let me work this part. Now we also had that the Laplace transform of sine of kt was equal to k over s squared plus k squared. Now, if you look, the s has still been shifted, but now we're talking about a sine, and the k has to be a 5. So I don't have a 5 here to match the 5 that's here. How do I do that? Well, what I can do is get rid of this 1 and put a 5 here, so long as I multiply the front of it by 1/5. Now, that looks like an x, but let me get rid of the 1 so that we're no longer confused. This 5 matches, 5 could be k because then I have the same thing here, and then a shift to the left 3 places gives me e to the negative 3t sine of 5t. Here, let's try an inverse transform of 5s all over s minus 2 squared. And you always pull out the number part. That usually makes things a little bit easier. Well, here I have s over s minus 2 squared. Nowhere do we have anything that deals with an s being in the numerator in this format, at least. We haven't dealt with it yet. What I can do instead is the following. I can do a little algebraic manipulation. I would like to match this s minus 2 with s minus 2 in the numerator. So I will do s minus 2 in the numerator divided by s minus 2 squared, but then I subtracted 2, which means I actually subtracted 10, so I'll have to add 10 of that, 1 over s minus 2 squared. Now what we're going to use is going to be a variation on 1 over s. Let me cancel one of these s minus 2's out here, and this is what I have. I have 5 inverse transform of 1 over s minus 2 squared plus 10 times the Laplace, inverse Laplace, of 1 over s minus 2 squared. When I said I canceled that, I actually forgot to do it, didn't I? Now, let's recall a couple of things that we had here. The Laplace transform of the number 1 equals 1 over s. And the Laplace transform of t equals 1 over s squared. So in this problem here, they're just shifted to the right 2 units. Both of these can be read directly from that. Here, the 1 is not a big deal, but I will have an e to the 2t attached to it. So in this problem, I get 5, and so this would normally be t. That would normally be 1. E to the 2t. Now this would typically turn out to be t, but then we have the shifting to the right 2. I'm guessing a problem like this seems a little bit tricky, but the real shifting that's going on is always down here, mostly down here in the denominator. Up here, in order to work this, I'm just going to have to FOIL this thing out. So I get inverse transform of s squared plus 2s plus 1 all over s plus 2 to the 4th. And then I can try to get myself an s plus 2 to factor up here. It was only s plus 1. But then if I want that to work, say I want to get, from an s squared, I'm going to be able to get an s plus 2 squared if I do the following stuff. Just think for a minute. S plus 2 to the squared is s squared plus 4s plus 4. So if only this were a 4s and this were a 4. Well, I can make it a 4s by adding a 2s and then adding 3. That way, if you read across, I'll have s squared plus 4s plus 4. But what I added in here, to make up for just throwing that in there, I'll have to subtract it off. Alright, so let's see what we have then. For this, I'll go ahead and simplify. This is s plus 2 squared. There'll be a nice cancellation that can happen there. Now, as before, I would like to, like I did here, if I simplify this, I'll have a 1 over s plus 2 squared. And that, now that we've seen the shifting, is not so hard, because my model will be those transforms whose answer turned out to be 1 over s squared. This is just shifted to the left 2 units. Now here, I would really like to have an s plus 2 that I could cancel with down here. And if I try to factor out a 2 from these two things, I'll have an s plus 3 halves. Well, I can remedy that by simply adding 1 to it, but then you have to subtract that off. Now, before I go further, I want you to understand what happened here, because I'm going to fix something right now. When I added this 1 in here, technically speaking, I subtracted 1. So to make up for that, I'll put a plus here. And so then I'll get minus 2s plus 4 all over s plus 2 to the fourth plus inverse Laplace of 1 over s plus 2 to the fourth. I'm almost ready to start taking the inverses, but not just yet. If I factor this 2 out of here, I can. So we'll have the inverse Laplace of 1 over s plus 2 squared minus 2 inverse Laplace. When I factor the 2 out, I'll have s plus 2, but I'll cancel it from down there to get 1 over s plus 2 cubed. And then finally 1 over s plus 2 to the fourth. Now let me remind you of a few things. The things that ended up in 1 over s squared was the Laplace transform of t equals 1 over s squared. So this is just a shift to the left 2 units. So this part right here will be e to the negative 2t times t. Then here, for this next one, what's funny is I probably should have left the 2 there because it actually fits the format for something we found next. The Laplace transform of t squared equals 2 over s cubed. Remember, it equals that exponent factorial all over that exponent plus 1. So for this, I can take it back to t squared, but I'll have an e to the negative 2t attached to it. And for the last one, the general formula was the Laplace transform of t to the n was equal to n factorial all over s to the n plus 1. So for my last piece here, it would be nice if if n plus 1 is 4, then n must be 3. I would like to have a 3 factorial right here. That means I have to multiply the outside by 1 over 3 factorial. And then I'm going to get t cubed, but I'll have to have an e to the negative 2t attached to it. Example 8. Here, let's solve y double prime minus 4y prime plus 4y equals t cubed e to the 2t. And we have a couple of initial conditions. Y of 0 equals 0, and y prime of 0 equals 0. Very nice. Alright, as per usual, let's go ahead and take the Laplace transform of each side, and I'll use linearity. So I'll have the Laplace of y double prime minus 4 times the Laplace of y prime plus 4 times the Laplace of y equals the Laplace of t cubed e to the 2t. Normally, the Laplace of t cubed is 3 factorial all over s to the fourth. You do whatever the exponent is, that factorial, and then you've got plus 1 for the exponent. However, this e to the 2t tells us to shift to the right 2 units. So let me take that out of there and replace it with s minus 2 to the fourth. Over on the left, we have the usual stuff. F s squared, capital F of s, minus s y of 0, minus y prime of 0, minus 4 times sf of s minus y of 0 plus 4f of s. And of course, because of the initial conditions, all of these y of zeros and y primes of zeros disappear. I'll have s squared capital F of s minus 4s capital F of s plus 4 capital F of s. And that equals, you can leave the 3 factorial there if you want. You can call it 6 if you like, but I'll leave it there. And so on the left, I'll factor an f of s out of everything. I'll get s squared minus 4s plus 4 times f of s. This factors as s minus 2 squared f of s. So I'll divide by s minus 2 squared. That matches the other side. I'll get f of s equals 3 factorial all over s minus 2 to the 6th. Then y then will be the inverse Laplace of that. And of course, if you think the thing that works for the inverse Laplace to the 6th power is if I had a 5 factorial in the numerator. Well, 5 factorial equals 120, and 3 factorial equals 20. So what I need to do is multiply this by, it looks like 6. No, it already is 6. I need to multiply it by, oh, no wonder I'm getting myself mixed up. I need to multiply it by 20 to match 5 factorial. So I'll multiply out up here by 20, and I'll have to make up for it by multiplying out there by 20. But in the end then, what you get is I will get 1 over 20, the inverse Laplace of 5 factorial times s minus 2 to the 6th. And that's the exact format I need. Now then I'll be able to write the answer 1 over 20. Remember, the s minus 2 is a shift to the right 2 units, and we had that at the beginning anyway, so it's no surprise that it's there. I'll get my e to the 2t, but then I'll get times t, this 5 here tells me the exponent on the t, times t to the 5th. Alright, so as usual, I'll take the Laplace transform of each side. There should be a y there. And that'll be the Laplace transform of 1 plus the Laplace transform of t. And let's do our normal business here. We have s squared, capital F of s, minus s y of 0, minus y prime of 0, minus 2 times s f of s, capital F of s, minus y of 0, plus 5 times capital F of s. And I've already mentioned the Laplace transform of 1 is 1 over s. The Laplace transform of t is 1 over s squared. And let me clean up the left side here. I still have my s squared capital F of s y of 0 is 0, but y prime of 0 is 4, so I have minus 4 minus 2 s f of s. The y0, of course, is 0, so I don't have to worry about that. And then I have plus 5 f of s. And that equals 1 over s plus 1 over s squared. So let me go ahead and add this 4 to each side. On the left, then, I'll have s squared minus 2s plus 5 times capital F of s. And on the right, I'll have 1 over s plus 1 over s squared minus 4. Now, I don't know how many ways there are to approach this, but there are probably a lot. I'm going to approach perhaps in one way, and it may not be the most efficient way, but I think it is pretty basic in its ideas. So what I'm going to do is this. I'm going to write this all as one fraction. That means this fraction here will become s over s squared. I'll have 1 over s squared. I have minus 4 s squared over s squared. So that gives me s plus 1 minus 4s squared all over s squared. So then when I go to solve for capital F of s, I will have capital F of s will equal s plus 1 minus 4s squared divided by s squared times s squared minus 2s plus 5. Now, I'm not really sure why I chose this problem. Perhaps I chose it because some of the partial fractions can get kind of crazy. Let me explain what I mean. When you try to set this up according to partial fractions, whenever you have a repeated 0, like this s squared is like s minus 0 squared, you have to do this. I'll do a over s plus b over s squared. And then this piece right here is not able to be factored over the real numbers. In fact, if you were to try to find the zeros of this, they're imaginary. So this is what they call a non-factorable quadratic. So what that means in cases like this, personally, when I teach calculus 2, I avoid this situation just because it's a pain, but here we have to face it. Here you have to put for your unknown cs plus d. The reason why you do all this is so that when you multiply both sides by this quantity, you'll have enough things in front of s's and s squareds and s cubes in order to have enough options to be able to solve for each of the coefficients. Let me multiply through by all that stuff. And so what I'll get then, I'm going to rewrite this as negative 4s squared plus s plus 1. So I'm multiplying through by this denominator, and I'll have a times s squared minus 2s plus 5 plus b times s squared minus 2s plus 5 plus cs plus d times s squared. And now I'm going to try to see if I can figure out what the numbers are. Now, once again, I typically try to put the zeros of the factors in here to figure out each of the numbers a, b, c, and d, but not all of that is possible. But I can plug in s equals 0. If I plug in s equals 0 to both sides of this equation, the left side will become just 1. The right side, the a will the a term will be wiped out. The b term is simply 5b. And the CD term is wiped out. So I immediately get b equals 1/5. Now from here, you can plug different numbers in, but I find it a serious pain to try to get a, c, and d, because I'm going to have a series of 3 equations and 3 unknowns. So instead of all that, what I'm going to do is the following. I'm going to take this and keep it in mind. It's still valuable that I got the b equals 1/5. What I'm going to do next is negative 4s squared plus s plus 1. I happen to think it's easier to multiply everything out and match coefficients than it is to try to pick different numbers and find the numbers a, b, and all that way, because while I'm able to find b rather quickly, a, c, and d are a lot harder, because I can't put in imaginary or complex numbers that zero out this stuff, because over here I'm not guaranteed that it will clean up so nicely. So instead, let me go ahead and multiply everything out. I'll have an as cubed minus 2as squared plus 5a. And then for the b part, I already know that it's 1/5. So I have plus 1/5 s squared minus 2/5 s plus 1. And then over here I'll have plus cs cubed plus ds squared. Now, what I'm going to do is go ahead and take this stuff over here that I already know and subtract it off to the other side. I've just caught an error when I added the 4 here. Now let me go ahead and get rid of this stuff that I already know and subtract it to the other side. So 4 is like 20 over 5. When I subtract 1 over 5, I'll have 19 over 5 s squared. And then I'll be adding 2/5 s. So over here I'll have plus 7/5 s. And then the 1 and the 1 will cancel out. Now on the right, I'm going to look for everything attached to s cubed, and that is a and c. So I'll have a plus c s cubed. Now what is attached to s squared? Now remember, I've taken this stuff away. So that's on the other side now. Now attached to the s squared, I have a negative 2a plus d. And then what else is left? Plus 5as. Now that'll allow me to solve for a rather quickly, because when I look at the thing that's in front of s, I've got a 7/5, and the only thing in front of s here is 5a. So 5a equals 7/5. Tells me that a equals 7 over 25. Now if you look, there is no s to the third term here. So a plus c, this piece right here, is equal to 0. That tells me that a equals negative c, or that c equals negative 7 over 25. So I have b, a, c, and now I'm just looking for d. Now the last equation that I have here, in front of s squared, I have negative 2a plus d, and that must equal 19/5. Now, the a I found to be 7 over 25. So I have negative 14 over 25 plus d. I'm going to make this over 25, so this is 95 over 25. And I'll go ahead and add 14 over 25. And I'll get 109 over 25 equals d. So let me go ahead and write those out. A, that was 7 over 25. B is 1/5. C equals negative 7 over 25. And then D equals 109 over 25. So let's see, where were all these numbers associated with? Right here. Let me go ahead and bring this down. Let me go ahead and throw in my numbers then. And the way I'm going to write them, of course, is f of s equals, I'll bring the a in front so it's easy for the linearity properties. I'll have 7 over 25 times 1 over s plus, then the b is 1/5 times 1 over s squared. The c is negative, so let me go ahead and pull that out. Negative 7 over 25 times s all over s squared minus 2s plus 5. And then the d was 109 over 25, so I'll have plus 109 over 25 times 1 over s squared minus 2s plus 5. So when I go to do the inverse Laplace, before I do that, I am going to want to make, the first two parts are easy. I'll be able to get those easy. This one right here will be 1, this one right here will be t. But the other ones, they're going to be a little more complicated. I move my f of s over in anticipation for the complication to follow. I'm going to use completing the square again on these denominators. Now here, s squared minus 2s, it wants to have a plus 1 so that I can have s minus 1 squared. Well, then I can rewrite this as s minus 1 squared plus 4. Of course, your mind should be thinking, oh, this is 2 squared. I want to do the same thing to the other piece as well. 109 over 25 times 1 over s minus 1 squared plus 4. I'm almost ready to go, except if you'll recall, the Laplace transform of cosine had an s in the numerator and in the denominator, and then you had k squared. Sine had a k, then s squared and a k squared. So I want to try to mimic that. The only thing, though, is if I have an s up here, I need to match it with an s minus 1 down here. So what I'll do, since I need to have an s minus 1 occur up here, I'll put it there. And I'll rewrite the 4 as 2 squared in anticipation for the use of the Laplace, the inverse Laplace. Now, if I subtracted 1 here, I have to make up for it. So I have to add the same amount. And then the last part, I'll have plus 109 over 25 times 1 over s minus 1 squared plus 2 squared. Now, when I actually subtracted 1 here, because of the negative that was in front, I actually added. So let me make this a subtraction. And when I did that, there was a 7 over 25 out front, so I'll put it over here as well. I'm getting there, so this will be 7 over 25 times 1 over s plus 1 over 5 times 1 over s squared minus 7 over 25 times s minus 1 all over s minus 1 squared plus 2 squared. And then here, these are quite compatible. They have the same denominator and everything. 109 minus 7 will be 102, so I'll have plus 102 over 25 times 1 over s minus 1 squared plus 2 squared. Now let's take a look at the Laplace, the inverse transform. So my y will equal 7 over 25, the inverse Laplace of 1 over s, plus 1/5, the inverse Laplace, 1 over s squared, minus 7 over 25, inverse Laplace of s minus 1 divided by s minus 1 squared plus 2 squared, plus 102 over 25, inverse Laplace of 1 over s minus 1 squared plus 2 squared. And now let's see what they give us here. 7 over 25 times the inverse Laplace of 1 over s, as we know, is 1, plus 1/5 inverse Laplace of 1 over s squared is t. Now over here, this is cosine of 2t, except it's shifted to the right 1 unit. So I have negative 7 over 25 e to the negative t, negative 1t if you must think of it that way, cosine. And now remember, this 2 squared is k squared, so this is cosine of 2t. Now here, for the last piece, this would be sine of 2t, except it is shifted to the right 1 unit, and in sine there was a k in the numerator here. That means I should replace this with, not k actually, the k is 2, I should replace it with a 2. In order to do that, I need to change this 25 to a 50. And then when I've done that, this is going to be 51 over 25. Except I will have, I don't want to have that just yet, the shifting part of it, that's e to the t, not negative t. Sine of 2t. Here's a definition. The unit step function is defined as, let me put it underlined under the unit step function, as a curly kind of a U, and basically, I probably should have been a little more careful there, talking about shiftings. U, well, I'll use U of t. That will equal 0 if t is less than 0, and 1 if t is greater than or equal to 0. However, for us, this won't make any sense to have a function that's called 1 other than the function 1, because all of our integrals start at t equal to 0. So instead of this, scrap this, we use this definition. U of t minus a, that'll equal 0. This happens when t is between 0 and a, and then it's equal to 1 when t is greater than or equal to a. This will give us control over the outputs of functions. I'm going to get rid of this because I don't want this to be the definition that we're going to use. Instead, I'm going to use this one. And a, of course, is a positive number of some sort. For examples 10, 11, and 12, let f of t have the following graph. Just a rough sketch, nothing fancy. Of course, this is along the t-axis, and then this is ft. So, for various examples, I'm going to chop parts of the graph, and I want to try to figure out, using this thing, how to describe it. So, for my example 10, here's the graph I'm given. We're going to start and just stay 0, I guess, right about there. We'll stay, of course I didn't line them up, so we'll stay 0 until I get to A, and then we'll pick that part until I get to B, and then after B I want to go 0 again. So I'll try to make these solid so you can see that. So basically, here's the idea. We've got this function that has been turned off until you get to A, then it's on between A and B, and then it's off again. So the question is, how do I represent that using this thing? Well, we can easily do U of t minus A times f of t has the following graph. This is 0 until I get to A. Then after A it equals 1, in which case f of t takes over. However, it has no end. It will allow the function to go on forever. I don't want it to go on forever. I want it to stop when I get to B. So let me put this so we can separate these. How do I chop it so it stops anything that's after B? Well, it's still going to be f of t, so I could do u times t minus a f of t minus f of t. Now, if I subtract just f of t, you can imagine that what will happen is I'll get the negative of f of t on this portion, but then I will have f of t minus f of t here, so it's not doing what I want yet. But to get it to enact something at b, I could throw on here t minus b, because this part right here is going, this part right here, I'm going to write it up here, the f of t times u of t minus b, just this part of the graph will only let f start to happen after it gets to b. So it will do this. And it will be here like that. And it will be 0 until I get up to b. So how do I work this? Well, if I do u of t minus a, f of t, I won't have anything until I get to f of t. Until I get to a, that is. But then if I subtract this stuff off, this part right here will let it go on forever. And if I take away this portion of it, then I'll chop it. And what I'll be left with is just that middle part. And the rest of the stuff will be 0 until I get to A, and 0 after B. Remember, this is still referring to the same function as before. Here, I want to have the function until I get to B, and then I don't want anything after it. So how do I go ahead and take that? Well, the whole thing would be f of t. This whole thing is f of t. But I would like to subtract off this portion here and 0 it out. So what do I do for that? Well, I could do, let me have this piece. The part that leaves just from B on is this. And so, and this is f of t until I get to B. So in this part right here, let's go ahead and solid it so I know. This function here then is f of t times u of t minus b, because that only lets f start after b. And so if I want this and this to give me this, I need to take this graph and subtract this graph from it. So this one will be an f of t minus f of t times u t minus b. Now in this example, this time I would like to 0 out until I get to B. But not only that, I want the graph to start now at B, so I actually want to shift it B units to the right, and I want it to start after B units to the right. So how do I make that happen? Well, I can start the function at B by simply having f of t minus b. But now, what will it have before that? Well, we don't know, because I don't know what the domain is, unless I really did start it at 0, and then it would really start here. Safest way to make sure that you 0 out before you get to B is to put a u times t minus b in there as well. And that way, this shifts f, the graph to the right to B. So there's the new starting place. And this ensures that for B we have 0. Let A be positive. The Laplace transform of f of t minus a times u of t minus a, that equals e to the negative at times f of s. And that's the Laplace transform of just f itself. So, and the way you could do this, if you wanted to see how this actually works out, let's see, I've got my f of t minus a times u of t minus a. if you recall from the definition of the Laplace transform, whatever is inside of these curly brackets comes after the e to the negative st part. So I'll have my f of t minus a u of t minus a dt. Of course, the u of t minus a, make sure this thing doesn't start until you get to a. Then after that it's equal to 1. So this integral will be from a to infinity, e to the negative st, f of t minus a, the u part being 1. Now let's do a change of a variable. So what I'm going to do is allow v to equal t minus a, and then dv equals dt. And so I'll be able to make the change of variable that way. So we'll start by changing the limits of integration. When t is equal to a, v will equal 0. When t equals infinity, so will v. And then I'll have e. Now I'm going to replace the t portion of this with v plus a. E to the negative s times v plus a. But the f part will simply be f of v, and the dt part will be dv. And then I'm going to rewrite this as 0 to infinity, e to the negative sv times, and I'll pull out the e to the negative sa, f of v dv. And here you can see it. I have made a mistake right there. I can see that now that I'm doing the integral. You can see this whole thing is a function of, how would you call it? A function of s. I mean the entire integral is. So I can actually factor this out to the front, the e to the negative as integral from 0 to infinity, e to the negative sv, f of v dv. Well, this, if there were a t here instead of a v, and there could be a t in there, the variable of integration is absolutely immaterial. I could write this as negative e to the negative as, 0 to infinity, e to the negative st, f of t dt. This way you don't have to imagine what's going to come next. This here is e to the negative as, and this is the Laplace transform of f. Or better yet, e to the negative as times capital F of s. What this means then, where is the beginning of all this? There it is. The Laplace transform of f of t minus a, u of t minus a, equals that stuff. That means that when you reverse this, that means the inverse Laplace transform of e to the negative as, capital F of s, will equal f of t minus a, u of t minus a. For my last example, let's solve y double prime plus 4y equals f of t. And we have y of 0 equals 0, y prime of 0 equals negative 1. But here, f of t is a piecewise defined function. So here is a function that is 1 until we get to 1 and then 0 afterwards. For a quick look at this graph, if that's 1, until you get to 1, you have this, and then you have a hole there, but then you have a solid dot here, and it's solid from then on out. Now let me write this equation with this stuff in mind. I'll have y double prime plus 4y. Now that'll equal the number 1 until I get to t equals 1. And then I want to have plus u of t minus 1, because this tells me, well, actually, minus, because then I'll have 1 minus a 0 until I get to 1, and then I'll have 1 minus 1 after 1. Let's go ahead and take the Laplace transform. So the Laplace of y double prime plus 4 Laplace of y equals the Laplace of 1 minus the Laplace of u of t minus 1. Well, we know what the Laplace of 1 is, and that is 1 over s. Minus, and then here, the shifting is by 1. Let me follow this up here. Here, if you will, the f is not simply the number 1. That's not a problem there. So I'll have e, my a is 1 here, so I'll have e to the negative s. All over, and the Laplace of 1, which is 1 over s. Well, that's nice. Then let me go ahead and do my usual routine on the left side. I'll have s squared capital F of s minus sy of 0 minus y prime of 0 plus 4 capital F of s equals 1 over s minus e to the negative s over s. Let me plug in the numbers that I have. Y of 0 is 0, but y prime of 0 is negative 1. So it looks like s squared f of s. This part will zero out, but that'll be negative 1. So I'll get plus 1 plus 4 f of s equals 1 over s minus e to the negative s over s. Let me subtract 1 and at the same time factor out an s squared plus 4. So I'll have s squared plus 4 times f of s equals 1 over s minus e to the negative s over s. And then I think I'm going to divide by s squared plus 4. So f of s equals 1 over s times s squared plus 4 minus e to the negative s all over s times s squared plus 4. I'm going to go one step further, and this part right here, the e to the negative s, will come in handy in just a minute, but let me rewrite this. In fact, let me stop here for just a minute. And this is now perhaps the time that I want to discuss the Laplace tables that we'll be using. Ultimately, what I want to do right now, if I can, is I want to find the inverse Laplace of all of this stuff. So this will be the inverse Laplace of 1 over s times s squared plus 4 minus the inverse Laplace of e to the negative s all over s times s squared plus 4. Now, we have not done all the possible Laplace things. In fact, we've only scratched the surface of a few entries in the Laplace table. Let's go ahead and grab the table, and I want to compare it with what I have here and see if there's anything in the table that we can already use to get this answer. All right, in our current text that we're using for differential equations includes a table of Laplace transform. Every differential equations book has a table of Laplace transforms. Now what I'm going to do is come back to the problem, And look, I want to see if I got anything that looks like an s times s squared plus maybe a k squared if I'm lucky. So let's take a look in here and see if we see that. As I scroll down the table, if you look here, right here, this one right here looks like it might fit the bill. So let me go ahead and copy that. In the table, this here is y, but then this is f of s. So if you look, this is close to it. If you can imagine this 4, well, there's 4 right there, so it's attached to 1 squared. I could make that happen. And at the top, I would have to have a 2 times 1 squared. So let's take a look at that. In mine, I have the inverse transform of 1 over s times s squared plus 4. I am going to rewrite it. I need some space in the front of it. It would be nice if I had a k and all that in there. Let me see if I can make that happen. S squared. You see, plus 4k squared. Well, this is like 4 times 1. In fact, it could be thought of as 4 times 1 squared. If that's to happen, then I need to have a 1 squared in the numerator, so I have to have a 2 times 1 squared up there. What did I change? Well, the only thing I changed was put a 2 in the numerator, so I can make this 1/2. So now it matches. I can go, the reverse of this will give me sine squared 1t. So far my y equals sine squared t, that's 1t, divided by 2. Don't forget the 1/2 that is in front of it there. Now, as I'm going to try to fix these up, I forgot that I have a -1 over there. So this will have a -1 over s squared plus 4. Of course, I have minus inverse L'Hopital of 1 over s squared plus 4. And now, I've handled this part right here. Let me see if I can handle this part right here. So this part right here, let me go and see if I can find anywhere in the table that has an s squared maybe plus a k squared. I know that sine does actually, so I don't have to go very far on that one, but I'll bring it up nonetheless. Let me cordon off the area that I'm going to use for my answer. So let's work on this part here. So for my problem in particular, let's see what we have. I have inverse Laplace of 1 over s squared plus 4. So I need to work with the inverse Laplace of 1 over s squared plus 4. Well, one could imagine that the k in this case be a 2, so I have 2 squared. So I could write this as 1/2 inverse Laplace. That 1/2 out front is to put a 2 up here. And then I'll have s squared plus 2 squared here. And then I will get 1/2 sine of 2t. Actually, I believe it had a minus in front of it. So let me put that in front of there. And then all that's left is for me to deal with this e to the negative s business over s times s squared plus 4. So let's see what the table has in store for us there. So in anticipation of that, we are working this. Do I have a coefficient in front of it? I do not, but just I have a minus sign. And let me go ahead and find anything on the table that resembles this. So let's go ahead and take a look in the book. I don't see anything with an e to the negative s. E to the negative s, I don't see anything. There's more than just this page. There's 3 pages, I believe, of this stuff. Right here we have it. Right here, let me get it. I just found it. Here, we can think of this. Let me put the negative out front. Negative. Let me put my e to the negative, and in case I need it listed for me, the a in this case will be 1. And then I'll have times 1 over s times s squared plus 4. Well, then I'll know what the f of t is if I know what this is the f of s for something. The s times s squared plus 4. And I think we just did that, didn't we? There it is. That was sine squared of t over 2. So in our case, my f, in this case, that's the thing that comes back there, because here that was 4k squared. Remember, we just did that one there. However, I have to have f of t minus a, which the a is equal to 1. So I'm going to have this piece right here will be the negative sine squared t minus 1 times u of t minus a, u of t minus 1. And so I'll go ahead and append that to my final answer. Whoop, careful. That was sine squared of t over 2. So this I have to divide by 2, 1/2. And I'll have minus 1/2 sine squared of t minus 1 times u of t minus 1. And there is my final answer.